Hello and welcome to this small lecture on image filtering. Your host for today, Sunil Karamchandani. At the end of watching this video, the student should be able to relate the use of masking operations for filtering, comprehend the development of masks to enable low-pass filtering, and also to interpret the masks obtained for high-pass filtering. Now, before we actually go to comprehending the masks for low-pass and high-pass filtering, let us recall how image filtering is done. As we know that image filtering requires a masking operation. There is a mask and this mask has to be convolved with the image depending upon the size of the mask. So the size of the mask can replace 2 by 2, 3 by 3, 5 by 5, 7 by 7 and so on. That size of the mask will be convolved with that particular size of the image. Now, to develop this mask, first we have to understand the concept of what exactly in layman terms of filtering is. So when we talk about low pass and high pass filtering, what do we mean? Low pass filtering means summation or averaging, and high pass filter means differencing. So throughout this video, we would first see how this summing and differencing is actually going to be a low pass, first for one dimensional and then for two dimensional. Let's begin with low pass one dimensional with an array of 1, 2, 3, 4, 5, 6. Here what do is we have to low pass filter this. So it is an averaging. So it's an approximation. That approximation is done by averaging. So you take the first two, average them out. 3 and 4, average them out. 5 is take two elements, just take two consecutive and then leave, two consecutive, then leave. That is how you average it out. Now, whatever answer you get can be also visualized as the first element, say the answer is 1.5 for the first one, can be also visualized as the first element weighted by 1, added with the second element also weighted by 1. As you can see throughout this array, this is the similar procedure which is being followed to get these low pass values. So in a sense, we are developing a mask for low pass filtering as the coefficients of 1 and 1, which are the multiplying factors with these numbers, that divided by 2, saying it's averaged out. Now, this is for an array. Now, if you have to apply it to two-dimensional image, then you require these weights first for the rows and columns, and then divide by 4 to average it out. Similarly, this can extend to for a 3 by 3 mask as instead of 9 ones, 3 along the rows and 3 along the columns. Now, this is simple low pass filtering. What about if you required weighted? We required that some frequencies had to give more weighted, the other less. So there's something called this concept of weighted low pass filtering. Now, how do we do this? Let's consider the same array. Now, in the same array, now here we don't skip. Here we add the first two, 1 and 2, and then we add 2 and 3. So in a sense, the center value is repeated twice. Once again, whatever answer you get, you add it once again. Again, when you add, the center value you see is repeated here and repeated here. So in a sense that the center value we are giving more weight. So whatever answers we get from the second low pass filtering operation can also be interpreted as the first coefficient multiplied by 1, the last coefficient multiplied by 1, and the center one giving a higher weight. Now, if you observe throughout this array, we observe the same thing. The answer 5 can be obtained here by, if you take 4, 5, 6, center element by 2, 4 by 1, 6 by 1. And that averaged out divided by 4. So basically, we get a weighted low pass filter mask as 1 to 1 divided by 4, averaging out. Okay. Now again, we extend this from 1 dimension to 2 dimension. So we know that the unweighted mask is a series of 1s. So weighted mask will be 1 to 1 for the column, 1 to 1 for the row. So therefore, the center element only has the more weight, and all the adjoining elements have weight which is 1. And of course, when we come to two-dimensional, we also have the diagonal image. So we assign the same weights to the diagonal elements as we have assigned to the adjacent ones. However, you can make an exception to this. You have say the center pixel having more weight than the adjoining ones, and the diagonals having a slightly lesser weight than that. Now, same concept, we are going to repeat it in the case of high pass. Of course, 3x3 mask, we can go to 4x5 mask and a 7x7 mask, which is the same. Now, for high pass filtering, again we take this array, again we subtract, now divide by 2 in this case. Now divide by 2 is, we are just doing differencing. Then in this case, you know, we sometimes have to give, in a wavelet transform, we have to give the set of high pass and low pass coefficients. So sort of a normalization is maintained. So here it doesn't matter really, you divide by 2 or just take the difference. Again, whatever answers you get can also be obtained if you see, oh, I just clicked twice. So the first element by 1 and the second element weighted by -1 all throughout the array. So here the secret is out. Of course, the mask is half, 1 and -1. Again, same thing. We extend it to a 2-dimensional array. So therefore, you have let's see for the 2-dimensional. Let's again take another array 1, 5, 7, 8. Now in this case, you have second element subtracted from the first, the third element from the second, and the fourth element from the third. Again, this is going to repeat the second time. So second one is subtracted from the first, and so on. And therefore, you get the answer as the first element weighted by 1. The second element, you see, 5 is repeated twice. Here 7 is repeated twice. So here you get the answer as the first element having weight 1, last element having weight 1, and the center element having weight of -2, again giving you a mask of 1, -2, 1. Now again the 2D mask, 1, -2, 1 along the column and 1, -2, 1 along the row will make an image. The image center row will be multiplied with these coefficients, and the center column coefficient will multiply by this, and therefore you add these two to get again next one as -4 with all the ones adjoining. Remember, high pass filtering, the sum of the coefficients has to come out to be 0. Now again, as I said, when we go to 2-dimensional, diagonals remain. So again, if you take this mask 1, -2, 1 as the diagonal elements, the left diagonal and the right diagonal, so these corresponding elements of the matrix will be multiplied with these weights. Now what we are going to do is, now we are going to combine all of them, the row, the column, the left diagonal, the right diagonal, giving you a mask as -8 at the center with all ones, again making the sum equal to 0. This of course is called as the derivative mask. This derivative is nothing but differences, f of x plus h minus f of x divided by h. Now when we multiply these elements with the image, either we get a large positive value, which means it's a light point on a dark background, or we get a large negative value, which will mean that it is a dark point on a light background. And of course, this is also used for image segmentation and so on. Okay, now let's compare the average and the derivative mask. Now, low pass mask is the average sum of all the mask elements divided by the size of the mask. High pass mask is sum of all the mask elements equals to 0. So basically, is there anything called as a high pass filter? Because if sum of all the elements, there is no low pass filtering. Correct? So high pass filtering means high pass filtering can be also viewed as no low pass filtering. So I end my presentation here saying that is high pass filtering really existing, or it is just a myth? It is just when no low pass filtering occurs, you can say that all the components can pass through. With this, I end my lecture. Thank you and goodbye.